Well, students, in the last class, we have studied Gaussian elimination method and modified Gaussian elimination method with partial pivoting for solving linear systems. Gaussian elimination method gives exact solution, and modified Gaussian elimination method with partial pivoting gives a very good approximation when implemented on a computer. When we have this method in hand, now the question is why at all we have to go for studying other methods for solving linear systems. Well, there is a big disadvantage in Gaussian elimination method. The disadvantage is in the time taken by the method to obtain the solution. In numerical analysis, it is not only important that we have to worry about the accuracy of a method, we have to also worry about the time taken by the method when it is implemented on a computer. A method may be very accurate, but if it takes abnormally more time to compute the solution, then those methods will anyway be considered as useless. One good example for that is the Gaussian elimination method. When you deal with big systems, then Gaussian elimination method becomes very costly in the sense that it takes a lot of time to compute the solution. Now the question is how to know how much time a method takes. Well, it is very simple to know this because the time taken by a computer to calculate the solution is going to be proportional to the number of operations involved in the method, right? Therefore, by counting the number of operations involved in a method, we can estimate how much time it can take to compute the solution. To see that Gaussian elimination method is very costly in computations, let us do the operation counting of the Gaussian elimination method. Let's do the operation counting only for naive Gaussian elimination method. Let's divide the method into three parts. The first one is the elimination step, where the matrix A is reduced to an upper triangular matrix. And when we do that, correspondingly, the right-hand side vector B was transformed to another vector, which we denote by B tilde, and that is the modification of the right-hand side. We'll consider it as the second part of the method. And final part of the method is to obtain the solution X bar from the upper triangular matrix. That is, you solve this system and get the solution X by the backward substitution process, right? These are the three parts of the method. Let us go to count the number of operations involved in each of these steps. Let us first consider the elimination step. We will count the number of additions, which also includes subtractions because we cannot segregate them, and then we will count the number of multiplications and divisions separately. If you recall, we never touched the first equation, therefore let's keep the first equation as it is. Let us come to the second equation. Here we do the elimination and make the first coefficient 0, right? To do this, we have to make some elementary row operations. What is that? First of all, we will find M21, and that is given by A21 divided by A11. Here you can see that one division is involved, right? Now we go to multiply M21 with the first equation, right? M21, and therefore how many multiplications are there? Well, there are n multiplications, and then we go to subtract the resulting equation with the second equation, right? So we subtract it with the second equation. So how many, therefore, addition or subtraction depending on the sign of the coefficient. So how many are there? There are again n addition or subtractions are there. Now here you have to understand a very important point, that after all this process, what we get is the first term coefficient is 0, right? You can see that whatever may be the precision that we use, we have to get the first coefficient as 0. Therefore, don't ask your computer to make this calculation because it may do some error and unnecessarily it will put you into problem. So you just assign this term as 0 by yourself and don't ask your computer to do this computation. And therefore, your number of multiplication is reduced to n minus 1 only. Similarly, the number of addition and subtraction is also reduced to n minus 1. So for the modification of this one equation, we have one division, n minus 1 multiplication, and n minus 1 addition or subtraction, right? Now, how many such equations are there? Well, you have n by n system that you have considered. Therefore, you have n equations. But as you know, the first one, we are not going to do any elimination. Therefore, there are remaining n minus 1 equations, right? So, you have totally n minus 1 square multiplications, n minus 1 square additions, and n minus 1 division, and that will make our step 1 and gives us the system where the column 1, starting from the second equation onwards, all the coefficients are 0, right? And correspondingly, the other terms will be modified. So in order to do this step 1 elimination, we need to perform this many calculations. Now, when you go to do the second step, you can see that equation 1 is kept as it is. Equation 2 from the step 1 is also kept as it is. In this, remember, you have the first term as 0 and the second term, which we generally denote by a to 2, superscript 2, x to 2, and so on, a to n, superscript 2, xn, right? So that is the right hand side. And similarly, third equation, fourth equation, up to nth equation we have. Now we see these two equations will not be touched for step 2, and you have totally n minus 1 terms to perform the other calculations for the second level of elimination. And in that, we have to again perform one division per equation. Therefore, n minus 2 divisions we have. And how many multiplications are there? Well, again, remember the second term from the third equation onwards are going to be 0. Okay. And therefore, you will not be performing any calculation for this column. That is the second column from the third equation onwards. From the third equation onwards. So, you will not be counting that operation. Remaining, you have n minus 2 multiplication per equation, and similarly n minus 2 addition or subtraction per equation, and there are n minus 2 such equations you have. Therefore, you have this much operations for the second step of elimination. Now, how many such steps we will go? Well, we have to go up to n minus 1 step, where you will have just one addition or subtraction, one multiplication, and one division, right? You can check that. And now just elimination step has the number of operations equal to the sum of all these numbers. That is, the total number of operations involved in the elimination step is therefore, you add all this, plus you add all this, plus you add all this. Okay. So when you add all this, you can see that that can be written in this form. It's a very elementary formula. And similarly, if you add all these numbers, its formula is given by this. And when you add all these numbers, your formula is given like this. So this is very elementary, right? So these are the formulas we have used in this final expression. Similarly, in the modification part of the right-hand side, that is B1, B2, and so on up to Bn, how many operations are involved? You just think and do it, and then continue with this video. to check whether your understanding is correct. Yes, your first equation has no modification, therefore there is no operation involved in it. Whereas in the second one, you have one multiplication, that because you will be multiplying m21 with this and then subtracting with this, and that will be equal to b22, right? Therefore, for the second equation, you have one multiplication. Remember, there is no division because that is already counted in the elimination part. Therefore, you don't go to count it once again here. You will be storing it in a variable and just using it in this multiplication. Therefore, there is only one multiplication and one addition or subtraction. So equation 2, right hand side, involves one multiplication and one addition or subtraction, right? And now how many such equations are there? There are n minus 1 such equations are there. Therefore, you have n minus 1 addition or subtraction and n minus 1 multiplication, no division, right? So addition alone will be the first step, will have n minus 1. Second step similarly will have n minus 2 addition and so on. And that can be written with this simple formula. And similarly, multiplication is also same. Well, division you don't need to count. And coming to the back substitution, you can check that you have this many addition and subtraction. You can just go now and check it. It's not very difficult for you once you understand the elimination part. That is the most difficult one. Once you understand that, the basic idea in operation counting, not only in this method, but also in any method, you can do similar. It's just counting carefully, taking into account of all the operations that are involved in the computation. And similarly, multiplication or division in the backward substitution are given like this. Now coming to the total number of operations involved in obtaining the solution. How much is that? It is nothing but the sum of all the operations that we have counted so far, right? Now, in the elimination part, we have counted the number of addition and subtraction like this. In the right hand side modification part, we have counted like this. And in the back substitution, we have counted like this. That simplifies to this form. And similarly, the multiplication and division both combined together comes to this much. Just add them all and just simplify them. That's all. Now, what we infer from this result? Number of multiplications and divisions involved only in elimination. Let us only take the elimination part and see. It is given by this is the multiplication and this is the division that we have seen already, right? Let us simplify and see this. It can be written like this. I'm just taking n cube outside and I can write like this. Now, my question is, how fast this goes to infinity as n goes to infinity? In other words, this is of big O of n cube. That's what is understood from these calculations. Apart from that, we have addition in the elimination part itself, plus we have addition, multiplication and division from our remaining steps which are given like this and so on. So I'm just taking only one small part of the method and that itself is growing with n cube, whereas the other parts are growing with n square. Okay, that itself is very big. So the conclusion of our operation counting is, even if we take only multiplication and division into consideration, we see that large value of n, the operation count required for Gaussian elimination method is approximately 1/3 into n cube times, right? This means that as n doubles, the cost of solving the linear system goes up by a factor of 8. Okay, so that is what we are inferring, and that is really very costly. And you can see that most of the cost is going into the elimination part. Okay, that is also one of the important point that we have to remember from the Gaussian elimination operation counting analysis. So to summarize, the operation counting in Gaussian elimination method implies that the elimination step, the number of operations is of big O of n cube. Okay, it's of order n cube. The right hand side modification, operation counting, is of order n square, and the backward substitution involves the operation count of order n square again. All these as n tends to infinity. Okay, these are just order analysis. Hence, once the elimination part is complete, you can see that the other two are relatively less burden for a computer. This is the major part. But altogether, if you see from here, you can clearly feel that Gaussian elimination is very costly. Just assume that we have a computer that takes 10 to the power of minus 9 seconds per operation. Now, roughly how long the computer takes to solve a system with dimension n is equal to 1 lakh using Gaussian elimination method? The answer is, you can see that it is 92 hours roughly. Same, instead of this, if I give you another computer, say it takes 10 to the power of minus 6, it means it is taking more time, right? It means the computer is little less powerful than this. Then the number of time that this computer takes is roughly 92,592 hours. It means what? It is nearly 10 years it takes to compute the solution. You may be wondering who will solve such a big system. But in large scale scientific computing, there are a lot of applications in which people come across such huge systems. In such problems, Gaussian elimination method is more or less impossible for people to use to solve on a computer. So we have to look for some other method that can minimize the cost of computing and thereby increase the efficiency computationally. Remember, the problem that we are facing now is entirely different from the accuracy of the method, right? Accuracy of a method is yet another problem that you have to worry about. But efficiency of the method is about the running time of the method. Let us take up the problem number 5 in exercise section of chapter 3. This problem is about counting the number of operations in the Gaussian elimination method for a specific system. That is, the system structure is already known to us, and therefore we can take the advantage of this information and make our program in such a way that all the redundant operations are not performed on the computer. What is the structure of the system given? Well, the structure of the system is that Aij is equal to 0 for all I greater than or equal to j plus 2. And you have the n cross n system. Now assume that you have developed a program based on naive Gaussian elimination method, where you have not computed those terms that you know that they are already 0. If that is so, then the question asks us to count the number of operations involved in the program. To do this, first let us explicitly write the system and see how it looks like under the condition given to us. See, for I is equal to 1, you can see that none of the terms satisfy your condition because I is 1 and j starts from 1 and goes till n. Therefore, j plus 2 starts from 3 and goes till n plus 2, right? So I is 1 and you only start with 3 on the right hand side. Therefore, none of the terms satisfy this condition. Therefore, in the first equation, we are not given any of the coefficients to be surely 0. So we have to retain all the terms in the first equation, and therefore our first equation will look like a11x1 plus a12x2 plus a13x3 and so on till a1n minus 2 xn minus 2 plus a1 n minus 1 xn minus 1 plus a n n xn equal to b1. Sorry, this is 1. And now come to the second equation, I is equal to 2. In this case, your left hand side is 2. Again, right hand side starts from 3 onwards. So none of the terms in the second equation also satisfies our condition. Therefore, we have to retain all the terms in the second equation also. Thereby, we have a21x1 plus a22x2 and so on. Now come to the third equation, I is equal to 3. You can see that I is 3, and on the other hand, you have j is 1. So it starts from 3, 4, 5 and so on. So first term alone satisfies the condition, and therefore we are given that the first term alone is surely 0. So you have the first term is 0 in the third equation, but second term onwards we are not given anything, and therefore we have to retain the second term onwards. It means a32x2 plus so on till a3n xn is equal to b3. Now fourth equation, you can see that the first term satisfies, second term satisfies, and third term will not satisfy because you have I is 4 and the third term is going to be 3 plus 2, that will become 5, right? So third term onwards it will not satisfy, but first two terms will satisfy. Therefore, first two terms will be 0, but the third term is not surely known to be 0. Therefore, we have to retain that term onwards. So our equation will look like this. And it goes on like this. When you come to the last term, I is equal to n, you can see that n is greater than or equal to, when j equal to 1, it is 3. When j equal to 2, it is 4 and so on. When j equal to n minus 2, you have n minus 2 plus 2, which is n. And then n minus 1 plus 2 is n plus 1. And then you have n plus 2. So up to here, all the terms satisfy our given condition, and therefore we are given that all these terms are going to vanish in our equation, and the last two terms alone are not given anything. Therefore, we have to retain those two terms. So how our last equation looks like, it is a n minus 1, that corresponds to this. That is j is equal to n minus 1, xn minus 1 plus a n xn is equal to bn. This is precisely the system that is given to us. Now we have to make use of the structure of this system and minimize our operations in the Gaussian elimination method. Well, in step 1, you can see that all these terms which are to be made 0 are already awarded to be 0 to us. Therefore, you don't ask your computer to perform elimination for these equations. Of course, you will not ask your computer to perform this calculation also, because although A21 is not given to be 0, but after your step 1, that term will become 0 as per the method. Okay. Therefore, of course, you have one division when you go to find M21, and when you go to subtract the terms with the second equation, you have n minus 1 addition or subtraction depending on the signs, right? That is what you have to perform for equation 2. Now, equation 3 onwards, you don't need to perform any operation because you are already given all these terms to be 0 as per the structure of the system. Therefore, in step 1, you only have this many operations. Similarly, in step 2, well, you would have made this equation to be something different like this, right? Everywhere superscript 2 we will write, but third equation onwards we are not disturbing because they are already given to be in the form that we want. In step 2, now you will perform only the calculation for the third equation, okay, because only this term is not given to be 0, whereas all other terms are given to be 0. So fourth equation onwards we will not touch, but only third equation one has to perform the elimination process. Therefore, again at this step, you have one division, n minus 2 multiplications, and n minus 2 additions or subtractions, right? So like that, it goes on. And at the step n, you have one division, one multiplication, and one addition or subtraction. So totally in the elimination process, you have addition equal to n into n minus 1 by 2, plus multiplication is n into n minus 1 by 2, plus division is n minus 1. Similarly, in the modification of the right hand side vector, we have addition or subtraction equal to n minus 1, and the multiplication and division is also given as n minus 1. I'm just skipping the details, you can see easily. And for the backward substitution, you have addition or subtraction equals n into n minus 1 by 2, and multiplication or division equals n into n plus 1 by 2. You have to check all this carefully, and in the exam, if it is asked, you have to give the full details. Therefore, the total number of operations involved in the Gaussian elimination method for this particular type of systems is given by 2 into n square plus 2n minus 3, that we can say is of order n square, right, as n tends to infinity. Whenever you are writing the big O or small o notation, it should always follow as what turns to what. We should not forget that. Another type of systems that occur often in applications is the tridiagonal system. So how the tridiagonal systems will look like? Let us consider an n cross n system whose coefficient matrix looks like this. This system is said to be a tridiagonal system if, first of all the diagonal elements need not be 0. That is, the diagonal of the system contains non-zero numbers, and similarly, the lower and the upper diagonal also contains non-zero values. That is, this part, which is the lower diagonal of the matrix, and similarly, the upper diagonal also should contain non-zero elements. All other elements should be 0. That is, all these should be 0. To visualize this matrix, the diagonal of the matrix contains non-zero elements, and similarly, the lower and the upper diagonals also contains non-zero elements. and rest all elements are zeros. Such matrices are called tridiagonal matrices. More precisely, let us use the notation alpha for the lower diagonal entry, beta for the diagonal entry, and gamma for the upper diagonal entry. Then we will have beta 1, gamma 1, and rest all will be 0. That is the first row. The second row will be alpha 2, beta 2, gamma 2, and all others are zeros. Like that, it goes on, and you have alpha n minus 1, beta n minus 1, gamma n minus 1. That is the n minus 1th row. And you have alpha n and beta n, and that is the nth row. When your system is a tridiagonal system with A, that is the coefficient matrix being a tridiagonal matrix, then your Gaussian elimination method can be made more efficient in terms of the computation time, and that is specifically called the Thomas method or Thomas algorithm. The Thomas method is nothing but the Gaussian elimination method for tridiagonal systems. Now, how we make use of this particular structure of the matrix A to make our Gaussian elimination method more efficient? Well, let us take the first equation. Equation 1 is given by beta 1 x1 plus gamma 1 x2 is equal to b1, right? You rewrite this as x1 plus e1 x2 equal to f1, where e1 is equal to gamma 1 by beta 1 and f1 is equal to b1 by beta 1. Well, from here you can clearly see that we need beta 1 to be not equal to 0 in order to make this method work. Equation 2 can be eliminated to the form x2 plus e2 x3 equal to f2. Remember, in the Gaussian elimination method, step 1, we will eliminate the x1 part of the equation from the second equation, right? Therefore, we will have x2, x3 and so on. But x4, x5 and all are as such 0 in our system. Therefore, after the first step, your equation 2 will be left out only with two terms, x2 and x3, whereas x1 is already eliminated. And x4 onwards, they are as such not in the equation. As per the tridiagonal structure, where you can check that E2 is given by gamma 2 divided by beta 2 minus alpha 2 into E1. See, E1 is already known to us. Alpha 2, beta 2 and gamma 2 are given in the matrix itself. Therefore, E2 can be fully obtained. And F2 is given by B2 minus alpha 2f1. You can observe that all are known to us. Again, f2 can be explicitly calculated. So in this way, we can see that at the jth step, we have to eliminate the j plus 1th equation and is given by xj plus 1 plus ej plus 1 into xj plus 2 equal to fj plus 2, right? Where you can check that E j plus 1 is equal to gamma j plus 1 divided by beta j plus 1 minus alpha j plus 1 into Ej, where Ej is already computed when we are at the jth step because it was computed in the previous step, just like how E1 was calculated previously when we were calculating E2. Similarly, here also when we are calculating Ej plus 1, Ej is already calculated and we know it. And Fj plus 1, sorry, this is 1 here. Please note the change here, Fj plus 1. And that is given by Bj plus 1 minus alpha j plus 1 Fj divided by beta j plus 1 minus alpha j plus 1 into Ej. See, all these alpha, beta, gammas are coming from our matrix. and EJ and FJ are calculated in our previous step. Therefore, the entire equation can be computed with EJ plus 1 and FJ plus 1 given explicitly. Now you can continue this till the last equation, where the last but one equation is given by n minus 1 plus En minus 1 xn is equal to Fn minus 1, where En minus 1 is equal to, just you can get from the above expression, gamma n minus 1 divided by beta n minus 1 minus alpha n minus 1 into En minus 2. And similarly, Fn minus 1 is given by Bn minus 1 minus alpha n minus 1 Fn minus 2 divided by beta n minus 1 minus alpha n minus 1 into En minus 2, right? And the nth equation is given by alpha n En minus 1 minus beta n into xn is equal to alpha n Fn minus 1 minus Bn. So that will give us xn explicitly, and from here you can get xn minus 1, xn minus 2 till x1 by the backward substitution process. Sorry, this is x1 and not xn. This is the Thomas algorithm or Thomas method. We can observe that it is nothing but the Gaussian elimination method, where the tridiagonal structure is used cleverly to improve the efficiency drastically.